Hello again, students, and welcome to a new nugget on biomass for energy. As you know, this lesson deals with the system solutions, and we shall start by looking at some of the most fundamental things of the energy system. Let me first say that the energy supply system is one of the backbones in any modern society. If the energy supply system fails, then will the whole society stop working? Just consider what happens at a major electricity failure, or think about what would happen if there was no car fuel available. Because of that, there is a demand that the energy supply system contains a certain amount of redundancy. If the delivery of something fails or stops, then there will have to be a workaround or a replacement of some kind. Now, depending on how the system is organized, this can be met through multiple suppliers and by smart contracting. But it can also be met by using buffer storages. From a strict technical point of view, you would like to have the plants and the processes flexible. To some extent, that can be achieved by careful planning. And now you have to remember that I am not an economist, and I am not an expert in logistics and supply chain management. So what I will do is that I will discuss these things from an engineering point of view, an engineering standpoint. You are all well aware of the fact that energy is not the same thing as electricity. So let me start discussing the energy system from the perspective of heat supply to buildings. One way is to have a central energy conversion plant. In this plant is produced an energy carrier like hot water for district heating, or superheated steam, or electricity, or town gas, or anything else. This energy carrier is then distributed to the individual customers and used locally. Advantages are that the central plant can have advanced environmental control so as to minimize pollution. Risks and problems with the fuel storage can be minimized. Transports can be optimized because there is only one point of delivery. More advantages can be listed, but I will leave it at this right now. Drawbacks are mainly the risk for sabotage or a terrorist action. And that is because there is only one central point, and destroying that will completely stop the system. So, a system organized according to this philosophy will generally need several plants connected to the same distribution network. Just try to figure out how many power stations are connected to your national electricity grid. The main alternative is to have the primary fuel, oil, gas, wood pellets, methane gas bottles, or whatever, distributed among the customers. Each customer will then have their own boiler or whatever it is. This system is more robust with respect to terror because there are many individual supply chains, but on the other hand will it not include any real environmental control, and the need of transport work will be higher. So both ways to organize the energy system ends up with multiple production units. But the difference is that in the centralized system will the production units be bigger, and they will be able to take higher costs for environmental control. So the two general types of energy systems fit different types of areas. The centralized production is advantageous in cities, and in cities it can be used for heating and cooling production. In an industrial area, it can also be used to distribute superheated steam or compressed air or any other energy carrier that might lose quality if the time from producer to user is too long. For the king of energy carriers, that is electricity, is centralized production advantageous because it facilitates plants with a high thermodynamic efficiency. Decentralized production is advantageous in areas where the distance between the customers is long, or where the energy carrier may lose quality if distribution takes too long. District cooling, for example. If the producer pumps out cooling water at 5 degrees, but that water has become 18 degrees once it arrives at the customer, then it will not work as a cooling agent. So both systems have to be used in parallel, but in different areas. Within this course, we deal only with energy systems that are fuel-based. We do not go into hydroelectricity or wind power or solar heating systems or solar cells or anything like that. So for this course is the primary energy material biomass. In many cases, it will even be a biofuel. Being biological, it deteriorates. It is a more or less combustible substance already from start. It can catch fire and it can burn. To guarantee the delivery of energy to the customer, there will have to be buffers in several places throughout the supply system. Notice I say supply system, not supply chain. That is because the energy system cannot rely upon only one supplier and one supply chain. The supply of the primary energy carrier must be organized through a strategic alliance of suppliers, and it is up to the energy planner to form such an alliance. Talking about bioenergy and biomass, can this alliance be a farmers' cooperative? Or it can be a group of forest owners? Or it can be a set of food processing industries? Or it can be a number of algae farms? Or a combination? The important thing is that the primary supply is not left in the hands of one individual, be it a company or a person. It is also important to find a strategic mix of primary energy carriers. As an example, suppose you have set up your system based on straw as the primary energy carrier, and you have based your dimensioning on the average yield. Now suppose a year with a major crop failure. So even if you have planned your system to work also on corn stover, you might well run into problems on a bad year, because both resources are annual. What you would like is to build in a buffer in the system, like planning for some perennial fuel to be part of it, maybe wood residues. Even so, you should not base your planning on the average yield. The Gaussian distribution is such that if you assume that the annual yield should be at least the average, then you will be right 5 years out of 10. So you will be wrong every second year on average. But if you base your energy supply system on the average yield minus one standard deviation, then you will only experience a fuel shortage 1 or 2 years out of 10. So you want the energy raw material, the biomass, to be a mixture of annual and perennial materials. That way, can a low straw yield be balanced by, say, a large amount of wood residues because of a strong sawmill market that same year? The better you do this strategic planning, the more robust will the system become. But there will always be a need of buffers in the system. As soon as biological material is stored, it deteriorates. We will come back to that in a later nugget, but right now I only want to point out the importance of strategic thinking also when thinking about the buffers. So, as we just said, is a robust energy system one that uses multiple fuels or raw materials in multiple plants. That way, you will have reasonable guarantees that you always have enough raw material. And you will be reasonably safe for any madman or terrorist who wants to sabotage the system. But as you understand from what you have learned previously in this course, will this call for multiple processes to be used in the system. So to operate the plants in a local or regional bioenergy system, you will need process engineers from different sectors. To supply the system, you will need farmers, foresters, organic waste handling entrepreneurs. For the transports from primary producer to buffer storage and to energy plant, you will need local companies and transporters. A biomass-based energy supply system becomes relatively work-intensive, but the jobs are local and they are long-term. So when you want to convince local politicians about the advantages of bioenergy, do not forget to bring up this aspect. Now I only want to point you to two very useful handbooks that you shall download. These two handbooks are very much hands-on and describe more or less step by step how you shall proceed to introduce bioenergy on a local or a regional market. I will not exactly follow these handbooks in the lesson, but you will recognize the different steps and the concept. Now download the two handbooks, scan through them, and then proceed to the homework.